Welcome to the first episode of my podcast, Undergraduates Attacking Peer-Reviewed Nature Publications. Today our guest is Roger Koning Robert from the University of New South Wales in Sydney, Australia.
You can just call me Roger. I didn't know it was this kind of show, so I regret coming here.
Well, thanks for coming anyway. Today we're going to be discussing Roger's new paper, Decoding the Contents and Strength of Imagery Before Volitional Engagement. In it, Roger and his team come up with a daring claim that humans may not be fully in charge of choosing their own thoughts. That's a big claim, isn't it, Roger?
That is an incorrect interpretation of our paper. I see you're coming from the perspective based on Benjamin Levy's experiments on the readiness potential. In fact, in this paper, we believe our results are better explained by the hypothesis that weak sensory representations that exist before the point of conscious decision-making can actually inform the decision outcomes and not the other way around.
Okay, I see. Well, thanks for that clarification. Let's start off by diving a little bit deeper into each figure. Sound good to you?
All right.
Alright, let's start with figure 3, which shows you demonstrated the reliability of self-reported decision onset time before your novel independent psychophysics experiment.
That's right.
I noticed that you ran 2 ANOVA tests for both your binocular rivalry and imagery vividness tests in figures 3B and 3C. Since your data sets were coming from the same participants, why didn't you use a multivariate ANOVA where you had 2 dependent variables of priming and vividness? In that case, you would decrease the risk for type 1 errors and could see if there was any significant association between the 2 dependent variables.
That's a great question. We primarily conducted the ANOVA because we wanted to separate the priming and vividness Z-scores as independent events. Visually, we also thought that breaking up the analysis into 2 sections would make it more digestible for the reader. And third, we entertained the possibility that cognitive systems involved in priming may be significantly independent from those involved in the strength of visual stimuli, whether imagined or perceptual.
Well, if that was the rationale, instead of pseudo-randomizing free choice versus cued conditions to participants, could you not have assigned each subject to both conditions and perform a repeated measures ANOVA to account for the repeated measures taken for the same participants at different time points?
I see your point.
Alright then, well, let's move on to the real results. Let's look at figure 2. For searchlight decoding, I see you used a spherical searchlight paradigm. To account for variations in anatomical idiosyncrasies, you applied a constant spatial smoothing correction. Given the size differences in male heads versus female heads, would it not have been better to apply different correctional methods for each gender?
Well, I believe it was better to apply a consistent correctional method rather than to introduce additional variability in the inner participant voxel selection.
I see you provide your data points that are significant after correction for family-wise error rate because you perform a large number of one-sample t-tests. Instead of conducting these individual t-tests, did you consider a general linearized mixed effects model that accounted for time condition as an imagery or perception and participant as independent variables and decoding accuracy as a dependent variable? You could have taken inter-subject variability into account as a random effect as well.
Yes, we could have used that model, but we were mostly concerned with finding significant differences in decoding accuracies between time points. As such, we thought it would be best to evaluate each region of the brain individually for the different time points for both the imagery and perception conditions.
I see. Okay, so in figure 4, you wanted to demonstrate that if pre-imagery onset data from perception-related visual areas could predict imagery decision, you could implicate perception in the origin of predictive information, correct?
Yes, that's correct. Let me first address what you will probably raise questions on. Because in general, our results show that in perception imagery generalization, there was poor predictive power. We instead trained the classifier to pool the data points across the time points, measuring from before and after the onset in 5A and 5B.
Could it be possible that you were training the classifier using perceptual data, differential volumes of signal to noise, and therefore informative data originated from the different regions of the visual areas viewing the unattended images? Would that not influence the ability for the classifier to interpret signals from each visual area differently and account for the visual region-specific differences in decoding accuracy?
So I see you're saying that different regions of the brain that we looked at could have provided different amounts of useful information. Theoretically, yes. However, it is established in the literature that baseline differences within systems such as visual, motor, and cognitive are more negligible compared to inner system variability.
Okay. Well, lastly, you wanted to see if pre-imagery data could predict subjective, self-reported vividness rating, right, in Figure 6. I think this claim is probably the most believable, as it would make sense from a neuropsychological perspective, as you mentioned in the paper. Stronger patterns result in more vivid imagery.
I'm happy you're happy with this figure.
Alrighty then. Now we're going to move on to some more general questions about your paper.
Okay.
Let's first talk about your sampling methodology. In your methods section, you say that you had 14 participants, right? 9 of whom were female. Considering the breadth of your study, why didn't you expand your sample size?
Well, as researchers, we understand that the sampling could be considered small, but according to past literature in the field, 14 is a sufficient number of subjects.
Understandable, and we noticed some of your sources that you cited for that number of participants. But recently, in an article published by Nature Communications by Turner and colleagues, however, the authors advocate in favor of larger sample sizes to increase reproducibility in fMRI studies. Would you agree with these authors, as well as a growing number of researchers, that larger sample sizes yield more reliable data, especially in the era of the reproducibility crisis?
I understand Dr. Turner's approach, but if more participants were available, absolutely. But in some cases, that is simply not possible. We work within the constraints we were given. In fact, in the paper, we mentioned that a lot of the tasks require that the subjects be quite experienced in participating in psychological experiments.
I see, of course. Well, here's a fun question. Do you think your results would have been different if you had accounted for the gender of the participants?
I suppose that could be interesting. There are ample studies in the literature that have shown baseline differences, also known as default mode networks in fMRI, between men and women. However, the field is still divided. Weissman-Fogel and colleagues reported in 2010 that the baseline gender differences in default mode networks may actually not be real.
Interesting. Well, maybe. Who knows? Okay, I also wanted to ask you a question with regards to the breakthrough paper by Eklund and colleagues published in 2016 regarding the false positive rates found in fMRI data. How did you, in your study, minimize the rate of false positives?
Well, yes, that paper was an eye-opener for us in the computational neuroscience community. Luckily, a lot of the errors found in that body of work have been fixed, but we made sure we controlled for as much variability as we could. For example, we ran a permutation test to ensure all of our data were suitable for parametric statistical analysis.
That was a really nice touch, I'll add.
Thank you. We also did our best to account for any spillover effects with our N-1 control, as well as setting up a 10-second blank period in our first fMRI analysis.
Actually, I'm glad that you brought that up. I did have a question about how you accounted for potential participant bias in your first fMRI paradigm. Since you were testing participants an average of 9.2 times per approximately 7.07 runs, how do you know that after repeating such a rote task multiple times, participants weren't automatically imagining the same things over and over again? Therefore, the imagined grading wouldn't be necessarily random. If that were the case, you would continue getting similar activation patterns in the brain, and therefore you could be getting a higher decoding frequency when the frequency of the neural activation is based off of participant bias and not true random imagining.
That's a later question. Like I mentioned before, if we had access to more participants, we would have been able to run one person only once. I will acknowledge, though, as we did in the paper, that there was a slight bias towards switching gradings by the participants. It was above chance, almost 60%. However, we also mentioned that we rule out sequential dependencies by using results from classifiers trained on perception task only, eliminating participant bias.
I see. Well, not everything is perfect, right? I appreciate your response. Another question I had was regarding a potential control for your first fMRI experiment. Could you have asked participants to look at a blank black screen to test for resting brain activation and then trained your classifier based off of that data? In that case, I assume you would be able to compare relative activation levels in your experimental and control groups to ensure that the results you were seeing were truly based off of the introduction of the experimental variable.
I see what you mean, but we didn't think that it was necessary in our setup. Additionally, I don't really know if the classifier would have found anything useful out of data from just looking at blank screens compared to just resting state.
Understandable. Just a thought. Well, Thank you, Roger, for taking time to talk to us.
Thanks for having me, and I hope to never return.
Well, it was our pleasure to have you. Thank you all so much for tuning into our show. Join us next time when we'll be sitting down with Dr. Allison Lee Hilbun of Vanderbilt University on her paper, The Effects of Pain on Balancing Behavior, Complexity Analysis of Mediolateral Force Trajectories. Stay curious, my friends.